And we are back outside with our bicycle and our human power plant. And today we're going to be heating some water. So we have our setup, we have our bike all set up. You'll notice we have another attachment to our bike setup this week. It is our heating coil. And then we also have our beaker of water, which we have weighed out. And we have a thermometer here to track the temperature of it. So our thermometer is on, and we're reading in degrees Celsius.
Which that's about room temperature. Room temperature is like 21 degrees C, and that's kind of what we were shooting for here.
Yeah, so right now we're gonna try and raise that temperature by 5 degrees. While we're doing that, we're going to put our coil into the water. And now that we have our setup already, if we were trying to take a measurement here, we would be timing this as well. And we're going to be looking at the volts generated by our human power plant. So Audrey, whenever you're ready. All right, here we go, folks.
So Audrey's going to try and do her level best at pedaling, heating up this water, which, as we'll talk about in lecture, water has a pretty high specific heat, which means that it's actually kind of hard to heat up. So as this heating coil is warming and warming the water, over time we should start to see these values change a little bit. Courtney can be the recorder in the stir, but yeah, so we can use what Audrey's doing here. In fact, let's switch over here. So we're seeing Audrey's generating somewhere in the realm of, I don't know,
8, something like that.
Around 7 or 8 volts.
Yeah.
Down here, she's at maybe about 4 amps. Courtney's holding the board because it's windy and we don't want it to blow away. What I can do though is, and what Courtney can do, now if you were doing this yourself, we would ask you to stir the water every now and again, make sure it heats evenly through, make sure that heating coil stays in there. You obviously don't want the heating coil and the thermometer itself to touch because that would give you an inaccurate reading.
Yeah.
But over time, slowly but surely, the water is increasing in temperature, so we've gained about 1 degree C.
How's it feeling over there, Audrey?
Audrey, that's 1 degree Celsius. How you doing?
My knees are too old for this.
Your knees are too old. If you're too old, that means I'm screwed. So we're not going to make Audrey go all the way to 5 degrees C, because as you can see, this is a lot of work. So if you were doing this in lab, we would have, you'd probably want to switch off. One team member bikes for a little while, another team member hops on, bikes some more. And in the meantime, we would be recording the time that it takes for this to happen too. So we want to know both, voltage and current to get power, and then time is going to give us energy. What are we at temperature-wise now, Courtney?
We're at 24.4 degrees Celsius.
So again, slowly but surely the water's heating up. So this is giving you an indication of just how difficult it is to heat up water. And then you can think about that in the context of all the ways in which you use hot water to take a shower, take a bath, make coffee, make tea, make pasta, do things in saucepans. It takes a lot of energy. Whether or not that energy is coming from electricity, whether it's coming from a natural gas flame, it's all energy use.
This makes me appreciate hot water more.
Audrey, are you ready for the Tour de France now?
Here I go.
All right. Oh yeah. Let's do one last temperature check and then
We went down 0.1 degrees Celsius.
we're going down.
5 whole degrees Celsius, I definitely made it there.
So last we left off, we said that we went down 1.1 degrees Celsius. We're outside, and I don't know if you can tell right now, but it's pretty windy out here. So there's a chance we might have lost some heat to the atmosphere. Unfortunately, I was not a very dedicated stirrer.
Yeah, notice there's no cover to these beakers, so
Yeah.
heat can get lost to the surrounding environment.
Yeah, and it's probably not being as uniformly heated as we would want because we're not constantly stirring.
Yes, and actually sources of heat loss and inefficiency are part of what you'll be exploring in this lab activity. So this is actually kind of a good point to make, that there is heat lost if you don't cover your water as you're heating it. So keep that in mind when you're making pasta or making coffee.
Also, if you make pasta or coffee outside in the middle of a bunch of wind, it might not be great for your efficiency.
If you're dining al fresco.
It may take longer than you think.
All right, TAs, any closing thoughts?
Good luck in lab today. You'll
Yeah.
see more videos from us.
Hello! So in this lab we're going to focus on heating water and the efficiencies that can come with that and the inefficiencies, of course. So we're going to start by learning how to measure water and take the weight of it and all kinds of things. So if you want to take a look over here, we've got our empty beaker and a scale. Scale starts at 0 and with the empty beaker, 219 grams. Perfect. So I'm going to fill this with a set amount of water, and that's 400 milliliters. This is going to be consistent throughout our test today. All right, 400 milliliters, we're going to give it away. 622 grams, so that's just over 400 grams. We're also going to take the starting temperature. That'll probably be somewhere around room temperature, and we're taking it in Celsius. Let's give it a go. All right, 24.4 degrees Celsius, great. So those will be our starting data for the test today.
All right, so we have our water pre-weighed, and now we're going to take the initial temperature of our water. And we are right at 24.3 degrees Celsius. So I'm going to take the thermometer out of our water, and I'm going to throw this into the microwave. So we have our watt meter right here. And before I get the microwave started, I'm going to make sure that my watt meter is set up correctly. So we want to have this reading in watt hours, which it is right now. And then we're going to pick a time that's less than 1 minute. So Audrey, what time do you think we should start with?
45 seconds.
45 seconds. And we're looking to get an 8-degree temperature change. So while this is going, I want you to think about where there might be inefficiencies in this microwave system and how long it typically takes to heat up your water in the microwave. I know for myself, sometimes if I'm making a mug of hot cocoa or something, I'll throw some water in the microwave and it takes about 2 minutes before it's boiling. So hopefully it won't take too long. And while we're waiting on this, Audrey has a little story time.
I do, it's true. So we had a student back in the day that didn't know that thermometers, these things here, you see that metal? See the technical equipment? Metal? The student didn't know the thermometer couldn't go in the microwave and came back with a little melted thermometer one time. We wouldn't recommend that. Don't try it at home.
All right, so now that we have this out of the microwave, we're going to take the temperature again. And if you can see that there, we are at 41.7, 41.8 degrees Celsius, which definitely gave us that temperature change that we were looking for.
So with this lab, you want to focus on temperature change and energy used. What kind of energy did we use? Wow, 16.4 watt hours. It's a lot of energy to heat water. All right, so we've got new water and it's room temperature again. We just took the temperature reading and now we've got it on a hot plate. We're going to use this watts up meter to measure how much energy we need to heat the water.
And are we in the right unit?
No! Thanks. This is watts and we want watt hours.
All right, so we're gonna let that go for a little bit once we turn the hot plate on.
We put it on a nice medium setting. We're gonna let it sit and we'll come back to you with the final temperature reading.
But even as that's going, you can see that our watts up meter is registering how much energy this is using.
Let's see if there's been a temperature change in the 10 seconds we've been here. Not yet. We'll keep trying.
And this water started off a little bit colder, so we won't get it to quite as high of a temperature as we did for the microwave. All right, so while we have our hot plate going, we're going to talk a little bit about the calculations that you're going to do during this experiment. You're going to have two sets of calculations. One which is theoretical, where you will use values that are, what you would expect based on E equals MC delta T. The other one is going to be your experimental value, which is calculated based on the data that you have in the experimental data section of this lab. So you're all going to have the same set of data that we provide to you, but that's going to be the data that you would have collected with, the hot plate and the microwave and the bike if you were actually in lab.
Let's take a reading. How we doing? So we've used 37.9 watt hours.
And let's see what our temperature is.
Yeah, it sounds like it's getting warmer.
Oh yeah, I think we've definitely hit that.
Wow, substantially. That's over a 10-degree change.
Yeah. But you'll notice that for this, our watt meter is reading a lot more than we had for our microwave, and our microwave got us a much bigger temperature change. One other thing to note is that if I get close, but not too close to the hot plate, still staying away for safety's sake, I can feel heat radiating off of the hot plate. So even if I'm out here, I can feel the heat coming off of the hot plate.
Good thing to note for the lab.